Hello everyone, in this video we're going to review the normal stress due to bending moment. You can also call it bending stress due to moment. So let's see what are bending deformations of a straight beams. So the key driving force is actually the moment. If we apply a moment on a straight beam, the beam will effectively deform like the figure showing here. Okay, so if you imagine the beam is composed of many longitudinal fibers parallel to the axis. For example, the axis is along these directions, and the elongation of the bottom fibers, as I am showing in this figure, the bottom half, you can see the fibers are elongated. However, on the top half, the fibers are shortened. Okay, this will generate tension on the bottom and compression at the top. And there must be a transition where you have a negative stress go to zero and then from zero to positive stress. So that's why we will always have a neutral axis or neutral plane where the fibers neither elongate or shortens, right? Have this kind of understanding will help you understanding how we can derive the bending equations. The beam bending equations is starting to look at the geometric relationship. At the beginning is a straight beam, okay? If you look at the top section, it will equal to bottom, and it will equal to any arbitrary position. For example, y is the distance from the arbitrary location to the neutral axis. But what if we apply moment to the beam? You will generate these ununiform distributions. On the top, the fiber is shortened, and you can see the fiber length is reduced. On the bottom, you can see the fiber is elongated. And if you just take a look at the position y, and now it's changing from the original distance. We know the original distance OO should be equal to the one in the neutral axis at the original undeformed state. So OO still is OO. But the BB now, if we use a straight line to denote that, it's no longer equal to your arc length, right? So use a geometric relationship, we can derive the beam bending equations. If you want to know more detail, just look at the other video, our previous video, which show you the derivations. Here I'm just showing the final equation, which is the bending stress is equal to the moment you applied times the distance, the ending locations along the beam thickness directions, divided by the Iz, okay? We assume this is the Z axis. So this is the second moment of area. Now, if we just substitute some of the values of y, so essentially looking at any arbitrary positions along the beam, what happens on the bending stress? Let's start from the neutral axis. When we substitute y equal to 0, we get sigma equal to 0. So the stress at this point is 0. Okay, no tension, no compression. Above the neutral axis, in this case, we denote the y is downward. So above the neutral axis at any position here, which is also denote any areas above the neutral axis, we will have y is minus. Y is minus will indicate sigma is minus. Okay, that's exactly true for, we know it's under compression. Okay, and similarly, if you look at the bottom half where y is positive, and then sigma in this case is also positive under tension. Okay, so most of the time we just need to know how to use the bending equations here. If we know the moment and we know the y, and we can find the stress. If you ask me where I can find the maximum stress, either in bending, or either in compression, or either in tension, you can see it's a linear relationship. It's going from 0 going up, or from here is similarly. So the maximum bending stress, sigma maximum, must be at the edge where you have the maximum y. So y, for instance, you have a distance here is half h. So this will be equal to half h over Iz. The Iz is the cross-section. If you have different cross-section, the beam normally is in 3D. If I draw it, okay, you will have different cross-sections. For example, in this case, this is a rectangular shape. Okay, you will have Iz given by 12bh cubed. Okay, but sometimes you will get something like I shape, and then you need to calculate Iz separately. Okay. So let's look at an example just to help us understanding how to actually determine the maximum bending stress if you are given a typical beam bending problem. So in this case, it is a simply supported beam which has a cross-section as an I-beam. And we need to determine the absolute maximum bending stress in the beam and draw the stress distributions over the cross-sections, okay, at any locations. So let's start from these 4 steps. Step 1, we simply calculate the support reactions and internal force moment, because eventually what we want to do is calculate sigma. But we need to know the moments, and we need to know the y over Iz. So we need to find this term, me, moment, and y is maximum. It should be the edge of the beam, and Iz is the second moment area of this I-beam. Okay, we need to do them separately. Here, I just directly give you the Iz. Okay, that's worked it out already. And now let's focus on how to get Me. Okay, Me essentially for a beam bending problem like this. Do you remember we have discussed calculate the internal force, internal shear force, and the moment. So essentially the moments will vary across the beam. You want to find the maximum moment in any of the position, but you need to find the maximum first of all, maximum moment first. Using the maximum moment times the maximum y, which will give you the maximum stress. Okay. Let's start from the step 1. Step 1, simply draw a free body diagram. When you simplify this distributed load, let's define intensity for this distributed load as W. Okay, this can be simplified as a concentrated load moving downwards and has a magnitude. Let's say the distance here is L. It should be equal to W times L. And because a uniform distribution, so it will acting as in the middle of the beam, so half L. And we define the assumed support reactions, let's say Fxa, and this is the one Fya. And for point B, okay, we defined, because there's only one restricted degree of freedoms, so that means this is only have one reaction force, which is Fyb. So using the force balance, first of all, is all the force in the x direction will give us Fxa equal to 0, and Fy, all the force in the y directions, equal to 0. So we have a coordinate going downwards, so all these force I define are meant to give a positive value. So let's just put a plus sign for Fya plus Fyb and plus WL equal to 0. Okay, so this will give us one equation. Is not able to solve Fya and Fyb. There are two unknowns. So let's calculate another moment balance. So at point A, we calculate the moment against z-axis. Z-axis out of plane axis. We can work it out. So the moment for this case should be the concentrated load here, omega L, times the distance, half L. Okay, and there's another force here, because this force trying to push the beam moving clockwise, so there's a minus sign here, and similarly here there's a minus sign for Fyb times the total distance L equal to 0. Okay, from these two equations, okay, you can easily get Fyb is equal to cancel the 2L, and that will equal to half W over L with a minus sign, and Fya is same. Okay, so that's step 1 finished. We finished the support reactions, but we need to calculate internal force and moment. So to do that, we always need to do a cut, right? Cut any position. Okay, so suppose we cut any positions along the beam, and the distance from that to point A is x. And we can define the internal force Vx, Nx, and a moment Mx. Okay, I don't know these three values, but I already know the reaction force for here, which you know you can put these two values here. One is Fxa, the other one is Fya. Okay, then again use these three equations, force balance. Let's use them again. Use Fx equal to 0. We find out Nx, the normal force, is 0, and Fy equal to 0, and we found Fay plus Vx equal to 0. That gives us Vx will equal to the minus Fya, which essentially is WL over 2. Okay, and the moment balance again, that gives us the moment calculated against a reference point A. And so in this case, we only need to remember, I think one thing I missed is when we're doing this card, that doesn't mean the distributed loads is ignored. So for this case, this distributed load can still, still you need to consider it, and you still need to actually simplify the case. So now I'm simplifying the distributed load in this case by a concentrated load with Wx as a magnitude with the half x2 as the distance. Okay, so in this case we have missed one term when we're doing this calculation here, so I need just redo this. This is very easy to forget, so let's remember to add it. Okay, so Wx equal to 0, and this gives us one equations, and using the moment balance we will get another equation, which is Wx, this concentrated load, trying to push it clockwise, there's minus sign here, Wx times x over 2. Okay, that's the moment generated by this force. And the Vx again is a minus sign, Vx times x. And you need to remember there is the assumed internal moment. This is the moment we're causing the bending, which is mx. We assume it's positive, so let's just plus mx equal to 0. So now you need to use these two equations to work out Vx and mx. So let's work out Vx first. As we know, okay, Vx in this case is equal to minus omega x and minus fay. Fay, that value is become plus omega L over 2. Okay, that's Vx. And we substitute that to the second equations. Let's see what we can get. And so that's the first things. And the second one, we substitute the Vx in. Essentially mx will be equal to the Vx times x plus half Wx squared. We just need to plug in the Vx in, so minus omega Wx plus half WL, and now you need times x in this one and plus Wx squared over 2. Let's further simplify this. Let's see, in this sense what we can get is we can cancel half of this, so that become half Wx squared with a minus sign because there's a minus sign here, so minus this one plus half of omega x times L. So you can take out the common term, which is half Wx. This will become L minus x. Right. So that's the answer for the internal force and the moments. And to calculate the bending stress, we only actually care about this term, moment. Anyway, we need to draw the force and the moment diagram. So let's use it. we can copy this equation again just to remind ourselves. Okay, Vx is minus Wx plus half WL, and moment is half Wx L minus x. Okay, now this is the equation actually denote any arbitrary position along the beam. You will follow these equations, right? But is that the only thing we need to consider? Right, yes. Effectively, this should be enough, because along the beam, the stress you cut on the left hand side will be no different with you cut on the right hand side. Okay, so use these two equations, you'll be able to draw the force and moment diagram. Okay, here I just show you directly, because you can imagine Vx is a linear equation. You can simply try two value. When x equal to 0, let's say Vx will equal to WL over 2, and mx will equal to 0. And when x equal to the center, okay, 3 meter, you get another value, Vx equal to Wx in this case is half L. Okay, that's half L. Then let's just plug in the symbol here. You will get 0. Okay, in that sense, at the middle point, shear force is 0. A moment is half L, so that is will become W over 4L times half L, so that gives us WL squared over 8. And you can try x equal to L. Okay, so Vx will equal to minus WL, mx will equal to 0 again. Okay, so this is a quadratic functions because x is quadratic. Okay, quadratic functions, and this is a linear functions. With this kind of three value, you can already plot for the shear force. You can already plot that should be like a linear functions with x, and for example, you want to plot that y in this case, and in this case y in the downward, depending on where you want to put the value of y, in downward or upwards. If it is in this case, so x equal to 0, y essentially is a Vx is positive, so it's something like that, and it passing when the half L is 0, and when it is equal to L, then that gives us a minus omega L over 2. So that gives us a linear equation for this case. For the moment, okay, it will very similar, but it's a quadratic function, so parabolic functions from 0 to 0, and you can imagine when x equal to half L, that will reach the maximum. So that's the final shape it should look like. Okay, I actually use a Python program to plot it, although I swap the directions. Y in this case is at the top, that's why all this shape is mirrored. Okay, and now from this diagram, you will find the maximum must be in the center of the beam. Okay, so just use that value mx, this term, for calculate the maximum bending stress. Okay, so now step 3, maximum bending moment is found as m at the center part, which give us the WL square over 8. Okay, and we know for a beam, if it is a rectangular shape, okay, it will follow the notations as we mentioned. It will have the maximum tensile stress at the edge and maximum compressive stress at the top. So to calculate the bending stress, maximum bending stress, we can simply use, okay, maximum times the y maximum over Iz. In this case, Ix. Okay, our neutral axis is this way, but Iz is, yeah, it should be Iz because essentially it's a 3D problem. 3D problem, okay, where you can visualize the beam in 3D. Okay, the Z axis should be go in these directions, X and Y. Okay, so it should be Iz. Okay, and in fact, for this case, is the I beam. The cross section is the I beam. So you can draw like this. If I visualize in 3D. Okay. In 3D, it's a bit difficult to draw. Anyway, we will try to draw it. Is the I beam. Okay. And this must be another one come here. Okay, I'm just drawing the top half, and the bottom half should have another part we should draw here. I don't have a good pen, so anyway, so it should look like that, I-beam. And we know I-beam, we already give you the Iz for the I-beam already. So you simply just substitute my, y should be the maximum distance from the I-beam's neutral axis to the edge. Okay, which if you go back to see the questions, it should have y max. It should be 150 plus 20, that's 170 millimeters. And yeah, so then you get the maximum bending stress. But also, if you want to go further to actually determine the stress distributions over the cross-section, for I-beam, you can imagine there's two different sections you need to consider, okay? On the top, you will have a shape different in the middle part, okay? So, in that sense, the moment still is fine, it's not changing. The y is changing, the Iz, okay. In that case, we need to think about whether that will need to be changed as well for I-beam. because IZ is always talking about you're looking at the IZ over the neutral axis. Okay, stress distributions over the cross sections. Alright, I just checked that doesn't matter of your cross-section shape, either rectangular shape or I-beam or circular shapes. When you calculate the IZ, it will be a constant as the bending rigidity against the bending moment. So in that sense, this will be fixed once you calculate the constant, and the stress, bending stress, now will only depend on the y. So that's why it will still follow this type of shape. Compression on top, tension on bottom. Okay. Now we substitute all the value in. And in our calculation, we found the maximum moment is equal to this value, and I z in this case is given by this value and times 170. You need to just be careful anyway. I will use millimeters and megapascals, so I convert everything in Newton and millimeter. The final answer will be in megapascal. Okay, that's done.